anyway, so I got to thinking over the weekend. Well, I was thinking for about a week, and actually all 5 of you guys actually ended up taking you back to the wall where I was writing things, and I started thinking, right, about just some simple ideas. How to relate a simple program, you know, to what we want to do, which is move something around in E8, right? Before worrying about projecting anything, you can just think, well, what are quasi-particles in a lattice, such as E8? You don't have to convert it to a quasicrystal in order to be a quasi-particle. And so I started thinking last week, well, I started thinking, well, for several years, I've been having a intuition that fractals, that is some principle in fractal mathematics, some mathematical tool, some fractals as examples, something about fractals is supposed to be related to our program. But I never knew what. It was just every couple of years there would be some sort of loud intuition that I would get, and I would never have much time to think deeply about exactly how fractals, you know, would relate to what we're doing, particularly the type of fractals that are generated by, for example, like iterative quadratic functions, fractals that you can do in the complex plane or the quaternionic or octonionic planes. And then we did that conference that Fong and I went to, where we presented Fong's work on, you know, what she was learning, and it was also some stuff that Ray was also thinking about how you can transform a quasi-crystal, such as a Fibonacci chain, into a proper fractal, you know, but you never did it with a typical quadratic function or typical iterative function. It was just a conversion of something that looked like it could be generated by such an iterative function. So that brought to mind a question for me, which is, well, if we think that in this paper we proved that this is a fractal, then is it true that all fractals that there is an iterative function, such as a quadratic function, related to all fractals, even if you didn't create the fractal object necessarily by that iterative function? Does it correlate to an iterative function? And so therefore, if we think we proved that that was a fractal, which we did that, we derived it by a Fourier transform process, right, that took the zeros and ones and then converted it to what we claimed was a proper fractal. So that was thoughts that from the past. And then recently, I paid attention to this book that my associate kind of person who I know. So if it's somebody in my circle like Mike Rios or Piero or someone I know, I pay extra attention to it because I figure maybe there's a reason why I know them. So I looked at this book, Quantum Fractals, from Heisenberg's uncertainty to Barnsley's fractality. And Ark is a kind of rather sophisticated mathematical physicist. So it's dense, and I couldn't understand it by perusing through it. But I could understand this book. So I began slowly reading this book and stopping along the way to watch lots of professor videos and just quality videos that explain truthful math, that accurately explain mathematics, but do it in a way that I can digest it, because it's not so dry in these videos. So I watch these videos, read another couple pages, get stuck, watch videos. So it takes a long time for me to get through a book like that. But I can do it with this. I can't really do it with this book. So then I said, all right, well, let me see if I can assign David to slowly absorb this book. And he stops along the way and programs little fractals, and he tries to just really own the information, because he's going to do a series of presentations on it. So he'll be able to get through it better than I. So now we're in this process where we want to experience David's talks over a series of weeks. And if we like the insights that we get from David's talks and leads to something, then we'll probably also invite David to go to the next level, the advanced level, and figure out how to absorb some things from this book and take us through another series of lectures. So that's fractals. And so then I've always claimed that any deterministic iterative algorithm that generates surprising emergent complexity after sufficiently large iterations can be modified by the insertion of what I call a hinge variable into the algorithm, and that such a hinge variable does not necessarily destroy the emergent complexity that you achieve after a large number of iterations. So the first time that I conjectured that was about 8 years ago, and we had a mathematician here, Garrett Sadler, who was able to try to falsify or prove my statement. And turned out that it was a very interesting thing that we took one of the 256 cellular automata, and we inserted a pretty simple hinge variable, and which is just sort of something that can be two or more choices of step or operational action, and ran it with a large number of iterations. And so we ran it normally without the hinge variable in a deterministic fashion, and we ran it with the hinge variable, same number of iterations. So my prediction or guess was that it would be 1, the same resolution of complexity, and 2, the same quality of complexity, that is the same basic pattern for a given cellular automata modified by a hinge variable. It turned out that the conjecture was correct. It was a pretty neat result, and we thought that it was novel, because every time we looked in the literature and the internet about cellular automata, and we look at books like Stephen Wolfram's New Kind of Science, it's always, all the ones I ever saw were always deterministic. So it turns out, though, that it wasn't a novel discovery, and that the people at Wolfram had already tried that and learned that you can have non-deterministic cellular automata that result in surprising emergent complexity. So then I conjectured that one could do the same thing with the Mandelbrot set. And then Ray did that exercise last week, and I'll be showing you an image of what the Mandelbrot set is with this random hinge variable. So you let a random number generator choose, right? Now, if a human chose action on the hinge variable, then the human can choose to do that action in what the human perceives to be random, or what the human perceives to be some notion of order. So, but a random number generator will always, of course, do it randomly. So I think about reality as a program that is non-deterministic, playing itself out, and that at first, when the universe begins the program evolution, it can, if it likes, choose the hinge variable actions randomly. Or it can have some devious scheme in mind for order to happen, some chosen pattern of events to happen in the future, such that it makes actually strategic choices early on, even though it could look random. But then, if it were philosophically possible for a subsystem of such an emergent program playing itself out to have some notion of sentience or free will, then in principle, that subprogram could somehow hijack the hinge variable and act upon it. Now, we certainly do this in the philosophy of quantum mechanics, right? In the philosophy of quantum mechanics, you can think of, if you like, you can think of the universe as having a universal function that, if there were no observers, would just play out, and it would be like a deterministic unitary evolution. But when we think about the Copenhagen interpretation and the idea that a measure must make several choices that are themselves non-deterministic. In other words, I'm going to choose a conjugate variable to measure. I'm going to choose if I'm going to measure in the first place. That's two choices. And then I have to choose when I'm going to measure. And then I have to choose where I'm going to measure. So what I was saying last is I said that if you just think about the Copenhagen philosophy or ontology, which is an interpretation of quantum mechanics, and you accept the idea that you have free will. So you do patterns of things. You pick ice cream flavors. You decide to say certain things. But it doesn't mean that you're doing that randomly, because you may do it by this abstraction of reason or desire or intention. And so it's not a radical New Age view in physics to presume that humans have free will and that consciousness exists. That's probably actually a status quo view. And it's probably true that it's a very small minority of physicists today who claim that humans don't have free will and are operating as a deterministic kind of thing where everything is determined, right? All right, well, if that's true, if there's this idea called free will, and that it's free will that chooses when to destroy an evolution of a unitary evolution and to replace it with a new function, then at a very deep level, it seems that consciousness, which determines the non-random choices of when to measure, would be the thing that renders, that essentially contaminates an otherwise ideally deterministic unitary evolution-based universe with non-determinism, right? That is the decisions on when to prematurely end a unitary evolution, when to replace one function with another, one wave function with another. So when you shift to the simple programs view and you decide that perhaps the statistics of quantum mechanics, the fine structure constant, the magnitude of the speed of light and so on are all secondary emergent epiphenomena from large iterations of a simple program, then you have to also say that the epiphenomenon of your consciousness and the free will is also emergent. And at that point, you can say, well, if my code is like most codes, like C++ or English, or any code you can think of, where codes are generally operated by code writers in order to express in C++ compression algorithm or a video game based on the syntactical degrees of freedom within the code, then we would say that in some sense, these free will choosers, which are emergent epiphenomena, they loop back to influence or act upon the hinge variable, or i.e. the syntax, in a code to help steer its evolution. So then a couple months ago, I tried to get us all jump-started into Stephen Wolfram's community. So the backstory of this is that one day Stephen Wolfram was here for like 5 hours with his son, and he and I were talking for hours into the night about physics, and he came to understand some of the essence of what we're trying to do, wherein I was explaining to him that we are trying to make a simple program that operates on the E8 root lattice. And I gave him my step-by-step motivation for that. And I said, look, this is the lattice associated with the largest exceptional Lie group. The limit of these numbers, the reals, complex, and quaternions and octonions. And so I'm just going to play it safe. And I'm going to figure I'm more likely to get all the necessary degrees of freedom algebraically to eventually recover gauge symmetry equations if I do that versus a lower dimensional subalgebra, right? And then one could say, well, no, you need to go up to even higher. And so that could be true. But I gave him my motivation on that. And we agreed that at least one could recover the gauge symmetry equations for the standard model within the algebraic stack of E8. And so therefore, by transforming this system into projective transforms, that one could recover, right, whatever clever gauge symmetry physics that one used from any of the subalgebras embedded within E8 or subroot lattices for that matter. So then that was about it, and I didn't really socialize with Stephen Wolfram that much. But then later, Stephen Wolfram connected me with Ray Oshheim, and I ended up hiring Ray. So that was a nice benefit from my meeting with Stephen. But then Stephen kind of helped me in another way, where he reached out to me, 4 months ago, at a time in his life when he was realizing, look, I'm in my early 60s, he was thinking, and I've spent my whole life trying to lay down this philosophy called a new kind of science, which is just trying to popularize the idea that maybe reality itself is a simple program, right? That was his argument. It was unconvincing to most people, physicists. Most physicists had a hard time with that. And yet there were still many, many people around the world who did appreciate the idea that maybe reality is a simple program. So then he got in for the next 25 years of his life into a new language paradigm in computation, the Wolfram language paradigm, right? So Stephen tends to think that his ideas are really big and important, kind of like how I think my ideas are really big and important, right? So he felt that this cellular automata, simple programs up to reality view, just the simple idea that it's super surprising to some people when they see radically complex levels of emergent structure and pattern occur with sufficiently large iterations of a simple program. And so then he had this dream to sort of set the world in motion with a kind of brute force search in the universe of simple programs to find these class of simple programs that approximates the behavior of reality, right? That approximates anything from Einstein field equation solutions to quantum statistics. And he always looked at it as a brute force thing, right? Because he kind of deduced, well, of course, there's a simple program that can approximate nature because the universe of simple programs is very large. And if all you demand is an approximation, well, then there would actually be a large set of such simple programs. But how to find them from the much larger, virtually infinite set of simple programs that do not closely approximate nature. So, he wanted to. He felt that crowdsourcing was the best way to do a brute force approach. So at one point, like I told you before, he did come to us when I was more associated with X Prize Foundation and Peter Diamandis, he did come to us once and he wanted to kind of set up a prize, you know, like $1 million prize for someone who could find a nice approximation in the universe of simple programs. But that didn't work out, that X Prize funding. And then another 8 years went by. And then Stephen felt that he was kind of complete with getting Wolfram language in place. And in his early 60s said, all right, I better do this now or I'll never do it. So he decides to set in motion this project, which is called A Project to Find the Fundamental Theory of Physics. And it is simply the project to search through the universe of simple programs to find the ones that are approximating physical reality. And that kickoff of that program, or that attempt to create a worldwide community of a new way of thinking, and a crowdsourced brute force approach, was that meeting, but was that process that we spent a couple days of our time participating on in that Zoom call. So then on Friday, I get this book and this note from Stephen, and he sent me, when he invited us to participate, he did say, if I had to guess, your group is probably going to be the group who has the highest probability of finding the simple program, because there are not a lot of people, well, there's nobody else really doing what we're doing, which is trying to take something like an object like the E8 root lattice and use quasicrystal mathematics to build our simple program, right? This is not what's done in physics, right? In physics is the art of taking observables and writing them down numerically, and then trying to find the relationships to other observables, right? How one thing becomes another, how fundamental things behave, not what fundamental things are, is one way to say it. And so this is a very radical view that Stephen Wolfram has, that the fundamental things are actually themselves the emergent epiphenomena of a simple program. And that's exactly what our group is audacious enough to try to pursue, what a simple program. The difference between Wolfram's followers and Wolfram and us is one really big difference, which is that we want to restrict ourselves to an almost infinitely smaller subset of simple programs, right? That is, the simple programs that can be run on the E8 root lattice with a particular eye toward quasicrystal mathematics. That's a very, very restrictive parameter. But there are still a very large set of simple programs, even with that restriction. And that is why, because Stephen, as a particle physicist, and also as a smart guy, I mean, he claims to be the youngest person to have a PhD in theoretical physics at age 20. There's another woman who recently got her PhD, a Chinese woman, at age 20, but the months still, at the month level, it's still Stephen. And then, I don't know, maybe there's somebody younger. It doesn't matter, right? The point is that Stephen's a bright guy and an outside the box thinker. And it's a nice kudo to have him say that he thinks that we probably have the best chance of anybody because he understands particle physics, you know, and he got it. He grokked the idea that I was saying that, look, Stephen, I'm gonna make a simple program. I want to try to explore the space of simple programs, restricting myself to E8. So this is another book that we could do a reading of. So I was thinking maybe we could saturate ourselves into a space of thought and mathematics and computation, because that's what you all have done in university. You took a huge amount of your early life and you saturated yourself in all sorts of formalisms and theories. But if we're gonna really take this formalism seriously, that is the space of programs, right? And you can reduce a lot of programs to kind of irreducible forms, like all of these iterative graph theoretic programs that create growing graphs, right? Growing in complexity, growing in connectivity and node units. That, for example, can be reduced to the irreducible trivalent graph representation. And the QSN happens to be a trivalent graph. You can look at the E8 lattice as a 240 valent graph, and then you can reduce it if you like, if you have a motivation to reduce it to its irreducible form at the trivalent graph level. So the point that I'm making in this set of sentences now is that there's a lot of approximations as well as isomorphisms, as well as transformations of things that at the end of the day, the patterns that we're talking about making form growing graphs that can be reduced to trivalent graphs. So maybe we take a whole sprint and study this book full time, like with a yellow highlighter, and come together a couple days a week for note comparisons or helping each other out, insights, and just invest 3 weeks of our life into saturating ourselves like a summer school kind of saturation or workshop saturation into what this community is thinking. Because right now, Stephen is making some big claims that I don't understand. He is saying that they were shocked recently. This is almost since our April Zoom call with them, I think, that they've been shocked by some results that they didn't expect to find so early in a kind of brute force looking around. And we should learn about what that is. And it relates to gravity and quantum mechanics. And Stephen talks about it being unexpected. We should learn about that. So I kind of have this kind of thing in 3 chunks, right? Not my presentation. These aren't the 3 chunks of my presentation. But we have this idea about fractals, right? Which are simple programs. We have this idea of hypergraph simple programs, some of which produce fractals, known fractals. And then we have this idea of simple programs that I'm going to start calling cycle clocks, and they're group theoretically inspired. Okay, so this will be a little bit of a long talk, and we'll let our sprint presentations run over into Tuesday morning, and it'll be my typical style of thinking carefully about every sentence I say, and therefore I have to write it down. So we will talk about several things today. And the overarching theme is the idea of an evolving trivalent graph network generated by a simple program that moves CEs around. So vector algebra unification physics, such as E8 unification physics, are about mathematically beautiful gauge symmetry equations, not exactly first principles. If reality is a cellular automaton or a fractal-like simple program, like Wolfram suggests, well, then gauge symmetry equations would be emergent from many iterations and not fundamental, because he doesn't start with graphs that are in spaces, right? He just it's in an abstraction of spaceless or geometry-free graph theory. Now, on the other hand, if reality is a cellular automaton or fractal-like simple program operating on the E8 root lattice, like I am suggesting, the ideal gauge symmetry equations would be fundamental, right? Because I start with something like a root vector polytope. And if one could correlate their gauge symmetry equations to the root vector polytope of some Lie algebra, then if that's what I start with, and then I get a simple program going, and then after countless iterations, right, physics emerges, and then we discover gauge symmetry physics ends up correlating to that root vector polytope in some way. Well, then I would have to say that unlike Stephen's view, I would have to put the gauge symmetry as very deeply fundamental. So my views on E8 are geometric, which leads me to focus on certain category theory, set, number, and group theoretic implications of the E8 root lattice. It allows me to focus on it, not deeply understand it, right? So by focusing on it, I can nibble around the edges and glean essences from time to time. And I can also make executive decisions of resource allocation and ask other people who can penetrate the mathematical density better than I. So I use those four concepts, right? So set theory, number theory, group theory, etc. I use those concepts to restrict my primitive notions of algebraic simple program patterns that I'm looking to explore on the E8 lattice. I believe that the greatest scientific achievement of mankind to date is the discovery of the standard model of particle physics, and two, vector algebra attempts at quantum gravity, such as heteronic string theory. Because heteronic string theory uses two copies of E8. So we have friends, including people who work here, who have gotten close to the deepness of what the gauge symmetry physics community in general is trying to converge toward, right? All these different people doing different things. So because any higher dimensional algebra is a stack of lower dimensional algebras and root lattices, the network of modern gauge symmetry theories contain many examples that can be converted into one another and others that are approximations of others. And it goes even further than that, right? Because once you start thinking about work that some people have done on the general unification of mathematics, which is to date an unfinished puzzle, then you can see how number theory, group theory, category theory, and set theory further expand the network of possible approximations and transformations of one theory relative to another. So think of all of these theories as a large family of approximately correct models that acts as a kind of emergent network, right, of tiles, where each theory is a tile, and they're all trying to self-organize or show us something deep about the model that nature is actually using. So what is this convergent, evolving network of gauge symmetry theories or quantum field theories trying to tell us? Well, for one thing, I think it's trying to tell us, hey, focus on the geometry underlying gauge symmetry equations, for one, right? The entire network of quantum field theories is like a mathematical Rubik's Cube of mix and match possibilities waiting for clever mathematical physicists to play with to create ever better theories to add to the emergent mosaic of theories. So Copernicus' epicycle model was superior to the less mathematically sophisticated models just before it. The result was an improvement. Newton's model was more mathematically sophisticated, but did not require deep axiomatic changes of Copernicus's assumptions. The result was again an improvement. By contrast, though, Einstein's model required deep ontological axiomatic changes. The result was, I would suggest, an even bigger improvement. So our simple program view requires deep axiomatic ontological changes to the assumptions of Einstein. This includes the transtemporal strange loop aspect of reality, the role of consciousness, right? That may be collapsing wave functions. And most profoundly, the idea that space-time and particles themselves are not fundamental and are emergent qualities of a simple program that is merely epiphenomena. The axioms of our approach, in my opinion, whether you're clear on them or have memorized them or see all of the implications, I believe I have articulated them well in a series of 4 papers, starting with a new approach to the hard problem and ending early this year with the self-stimulation hypothesis. If you read all 4 in order, that's the best way to deeply grasp the connection or the network of ideas. I've never read all 4 back to back, so maybe I don't deeply understand the connections either. But perhaps the gauge symmetry journey of mankind has so far reached 90% of its goal for everything except for gravity, right? Because after all, the standard model is telling us that neutrinos are massless, right? So let's just give it a 90%. And maybe we could say that 20 to 80% of the ideas on quantum gravity so far are close to true, right? That's a pretty big spread, so I'm trying to be conservative there, just to make a point that we're going deep and we're getting clues about quantum gravity, and we've got really good clues about everything excluding gravity. However, if the radical philosophy of the simple program picture and some of our axioms are true, the simple program will have to be discovered before the full quantum gravity picture is resolved. For example, if the modern view about the nature of time turned out to be a false assumption embedded deeply within general relativity, the failure to derive a compelling quantum gravity theory might continue until this misconception is remedied. It would be a waste of time, in that case, to create ever better versions of a quantum gravity theory patched up with brilliant mathematical cleverness to minimize the obstruction of a deep and fundamental but false building block assumption about time. Wolfram shares this view that without the discovery of the new assumptions, we will make incremental to moderate improvements over previous gauge symmetry quantum field theories, never getting very close to the deep ultimate theory until the correct rethinking of the fundamental assumptions is achieved. So as you know, I do not agree with the popular assumption of time and how Einstein ontologically interpreted the experimental invariance of C. I understand his logic. I understand the reasonableness, right, that led to his logic, such as the reasonableness that space-time is structureless, for example. That's reasonable. But what if it's wrong? Then how does that lead you into the deduction process that led to Einstein's deductive ontology? So we can all agree that at certain astrophysical limits, general relativity breaks down for galactic behavior. It ceases to predict. Numerically, these failures of prediction are exactly the values of unobserved dark energy and dark matter. Imagine a different timeline, a different history, in which Einstein did not lay down the new ontology in 1905. And the resulting advanced mathematics that came 10 years later in general relativity. So left only in this alternate timeline with Newtonian gravity, we then advance the technology of observation, right? And we realize, like, our machines get better. So we advance our observational technology, and then we realize that the Newtonian model starts to break down, but only in extreme cases of observation. In the absence of a deep new theory, what would we have done? Well, we would have used mathematical cleverness to plug the deviations. The value of the plugs would have been exactly the value of the Newtonian model's failure to predict. We would have patched it out. And people would rest in that alternate reality, people would have rested content with the fact that Newton's model is still the model of nature, even though we cannot actually observe the substance of the plugs, other than our observation that the Newtonian model fails in extreme cases, the pre-patched Newtonian model. So Copernicus was more sophisticated than his predecessors. He used his intellectual prowess to patch up the defects in astrophysical models that were deviating from observation, the way the planets were moving, their patterns of motion. But he did this without any deep axiomatic rethinking like Einstein did.
Wait, I think he actually did. Copernicus changed it from the Earth center to the Sun center. That was a huge shift.
Actually, I believe that was done before him. Ptolemy.
Ptolemy had the Earth center, and Copernicus threw that out and made it Sun center.
Let me suggest, just for the context of this, that is not the type of deep ontological shifts that I'm talking about. I'll acknowledge what you're saying, but I'll say that as I get further into this, I'm going to point out only two major ontological shifts that have occurred. And that was first in Einstein's relativistic thinking. It was super crazy and deep and just weird. And then it was the assumptions of quantum mechanics that were even more bizarre. These were very deep things. To stick with the general math and the general philosophy and just simply say something is the center versus not, it's a big deal. I mean, in terms of philosophy, sure, but I'm trying to draw out a different kind of, a different class of axiomatic shift other than, the idea that the Earth, the Sun, or the center of Milky Way or whatever is the proper center. So, but yeah, all of these improvements to models like Copernicus's, certainly they're involving changes in assumptions oftentimes, but I'm trying to just point out crazy ass, deep, almost philosophical, because whether the Earth is the center or the Sun is the center or something else is the center of the universe.
But the very fact that we can say that's not a big deal is because of him. He's the one who showed picking centers as a relative.
Yeah, I acknowledge it. I mean, certainly I can acknowledge what you're saying, but hopefully you.
That's okay.
Yeah. Well, what I'm going to try to argue to you guys is that quantum mechanics and general relativity were incredibly deep changes in assumption, whereas what Maxwell did, right, which was a huge advancement, it didn't really require the same radical change in kind of ontological assumptions about reality that quantum mechanics and general and special relativity required, but everything's a kind of nuanced gradation, so it's hard to really prove that where a phase transition to something that's just a slight change or a more trivial change versus some radical change. That's all that I acknowledge is a matter of opinion.
Yeah, there are Galileo Galilei, like a phase transition.
I don't know. It doesn't matter because it's missing my point. My point is that saying that we
want to focus on quantum and relative relativity.
And I want to say that when Stephen Wolfram or I claim that reality is a simple program and fundamental particles in space and time, these are not actually fundamental. They're emergent epiphenomena from a simple program. That's freaking crazy sounding. That is an example of something radical, like the radicalness of quantum mechanics. Okay. So in each era, okay, the staying power of a model is robust over time if that model makes predictions. The more predictions it makes, the more impressive and robust it is. all the famous models in the evolution of science made predictions. Or I should just say all of the good famous models.
All except for string theory.
Yeah, you're right. Good point. Right. So all of the all of the predictive famous models made predictions. So anyway, they all had staying power if they made predictions. So the staying power, it involves also a little bit of irrationality, right? So there's rationality in the staying power. Sometimes there's irrationality, and that irrationality flies in the face of the scientific method because it's based on the quirks of human ego and human self-interest. Yeah, how can it not be? But axiomatic paradigm shifts are more rare than the typical changes and lower level assumption evolutions in physical models. The last axiomatic shifts of this nature occurred about 100 years ago, in 1905 with special relativity, and in the 1920s with the axiomatic revolution of quantum field theory. So I believe that general relativity is, to our axiomatic paradigm of simple programs, what its axiomatic revolution was to the Newtonian paradigm. These things don't happen very often. Newtonian physics was and is powerfully predictive, just as general relativity is to an even greater degree. Electromagnetism is predictive, but breaks down at limits in highly controlled circumstances in a laboratory. An entirely new set of axioms or assumptions was necessary in the form of quantum mechanics in order to replace Maxwell's predictive theory with the more predictive quantum electrodynamics. In other words, before progress could be made, the powerful, logical, and predictive assumptions in Maxwell's electromagnetism had to be abandoned in favor of a set of seemingly ridiculous ontological implications from quantum mechanics. There is an axiomatic philosophy even deeper than those implied by quantum mechanics, wherein a simple program is the fundamental thing, and quantum mechanics is an approximation in the form of an emergent epiphenomena. We have our radical new assumptions. Now, let us hunt for the simple program that lies beneath the gauge symmetry equations of nature. That is truly the holy grail. If the self-simulation hypothesis were true, it would mean humans are trans-temporal, strange loop, complex systems, fantastically emergent feedback loops, living in higher dimensional time, right? Because if you're a strange loop across time, then at least at a subconscious level, right, there's something going on in the emergent structure of that feedback loop. And these creatures like us then can choose, if we please, to attempt to hack the code of nature from which we emerged. So we are made of this self-emergent code in this story, right? Our consciousness emerges from it, and then it tries, for some of us, to loop back all the way down to understanding the code from which everything emerged in the universal scale Ouroboros strange loop. I think that's just interesting, right? So wouldn't it be amazing, though, if this here, circa 2020 Earth, were the first time that it has happened in the evolution of the code of the universe. The first time the universe loops back into itself to understand its true digital Big Bang, which would be the inception of the non-deterministic simple program from which sentience can eventually emerge and loop back to discover the program itself. That would be a trippy thing, because if this were the first time that happened, and we were the front horse, the way Stephen Wolfram thinks, the way I think, well, gosh, what an honor, right? So I have an intuition that this is the case, as I said, and it makes me feel some emotions. These three emotions. So we must create a geometric program, perhaps using the subgroup cycling idea that comports with standard model gauge symmetry equations. So notice that I carefully left gravity out of the picture on that statement because I want to crawl before we walk. I believe there is a deep misconception about space and time, and not as deep a problem with the concepts implied by quantum mechanics. I kind of am saying that I think general relativity needs to be modified more than quantum mechanics. Just a hunch. Now, can someone here in this room creatively use their knowledge of gauge symmetry physics to create a simple program that moves the CE around in the E8 root lattice? This is not an easy challenge because anyone who does this will inevitably incorporate their modern assumptions about what time is, or not. So this presentation is my attempt to inspire you with thinking tools that could lead to the synthesis of what I would call a kind of group theoretic quantum field theory and simple programs respecting that group theoretic categorization that are playing out on the E8 root lattice and then being represented in various forms, because you can represent it, you can stay in the E8 and you still get the quasicrystal. There's no great reason to follow through with the projections necessarily if you can recover the same information from the E8. You can get out of geometry altogether, represent it in matrix representations. Maybe you can represent it in Stephen Wolfram's abstract hypergraph representation. But I believe that there are lots of representations. So, the power of simple programs.
Just a point on the video. You have this question on, you asked what is the problem is the move of the C, or the structure, the rules, and all the framework that make possible to move the C. It's like, do we want to know the mind, how the mind of who is operating the move works, or how the game works?
How the game works. What is the simple program, not what the mind is behind the simple program.
Yeah, it's like that old thought that says that it's not possible to tell the player from the game, the dancer from the dance. Like it's kind of the problem is more fundamental that because if you see someone play, but you cannot say who is playing, but you can understand the game.
Exactly. So if I showed you the output of an extremely simple iterative program, then it's absolutely conceivable that if that program were simple enough that you could reverse engineer, kind of guess your way in to a subset of simple programs that may have generated my simple output. And then you could test them all and see which ones most closely approximate the output. And in so doing, you would have discovered my simple program, but you would not have discovered my mind. So Frank, please hit the play button. We're going to watch a couple fractals just for aesthetic entertainment. Full screen?
Yeah, it's fine.
It's right there. Oh, it's hard to control it. This is just a couple very short fractals just so you can stop hearing me talk for a minute.
I presented this before, by the way.
Yes.
So anyway, there's, I'm going to keep playing it, but I want to just comment as you keep looking. So there's an infinite number of ways you can modify these types of programs like of this class, and many of the ways include obviously propagators, annihilators, creation operators, interactions, transformations of one thing to another.
Anyone else need a costume break?
You need to go to the bathroom.
Yeah.
You have to go. Okay, that Hans Zimmer music actually made that seem even more important than it already is. This is the last one. This music makes them seem more fun than they actually are. Yes. Okay, so you get the idea. There are an infinity of these things. Okay, so I think that we should explore simple programs that are based on E8.
Did Fawn want a bathroom break?
Oh, no, she was just asking if you guys did.
Yeah, I saw that you went. So.
I just grabbed my water. So our program space would be, let's stay in E8 for now, right? And whatever. I think first we should create a program in E8 and not worry about quasicrystals. Just stay up there. And then we can transform the representation up there to the emergent behavior down low.
Oh. That's weird.
And non-deterministic. Because any any one of the infinite universe of deterministic algorithms or simple programs can be modified in various ways. You can modify it into a probabilistic space that spreads out in your solution space a span of different weightings of probabilities and updates without having to actually do the update. You can make them have a specific next update that is non-deterministic. Okay, so I want to talk now about my first suggestion of a cycle particle. And you know, we've already talked a lot about it. It's this focus on the 24 cell. So I want to focus for a bit on why I admire D4 and the 24 cell. So 3 of the fundamental 4-dimensional subalgebras of E8 are Z4, which is like Ray tells me not a proper Lie, it's not a Lie algebra, but it's a sublattice, but you can also see it as an algebra of a network of 4 copies of Z1. Anyway, D4, A4, and Z4 are fundamental 4-dimensional subalgebras living in E8. But of those 3, D4 is the richest or the most complex. So its root vector polytope is the 24 cell. Now, the only regular polytope that has no regular analog in any dimension, as you all know, is the 24 cell. Because the cube, tetrahedron, and octahedron have regular analogs in all dimensions. And the icosahedron and dodecahedron have regular analogs in 4 dimensions. And the 24 cell is just all by itself, has no friends, no family. The 24 cell corresponds to the group SO8, which is the group acting on 8 dimensions. This paper is something that people might want to take a look at because it's on the octonionic representation of Clifford algebras. It's about the spinor reps where its triality quality manifests an SO8 structure. I found it interesting. Well, I found it worthy of putting up here because it's dealing in Clifford algebra, and I think that we should be learning and working with Clifford algebra. I have all kinds of reasons for that. Some probably not good and some okay. The SO8, in other words, spin 8 algebra, contains a non-abelian S3 symmetry acting upon its irreducible representations. In the relationship between E8 and D4, we clearly have more than enough mathematical machinery to do standard model gauge symmetry unification physics. And clearly, the word clearly is not something that everybody would agree with. But a lot of people we know, and probably a bunch of people in this room would agree with the word clearly. I have radical ideas, as I mentioned, about what time and space are, so I do not want to overcomplicate things now, not yet, not today at least, with general relativity gauge correlations, which can be coaxed out of SO8 when the time is right. I would like to relate the following ideas for now. Cycle particles based on group theory and graph theory, or group theoretic graph theory. And then simple programs to emergent physics. So E8 has a deep golden nature to it. The E8 root lattice has 10 parallel classes of the D4 root lattice. Group theoretically, we can decompose the symmetry of the Gaussian polytope into 10 subsymmetry groups of 8D divided by 2 is 4D. It is powerful to study graph theory, group theory, and set theory geometrically, right? So I've seen all kinds of people talking about this, the power of geometry to probe deeper things in graph theory, group and set theory. For example, the complete and undirected graph of 5 objects can be symbolically represented in 2 dimensions like that, where it does a pretty good job of geometrically explaining, as a symbol, you know, it does a good job of geometrically explaining the full set theoretic combinatorics of the integer 5. However, it is not as helpful a symbol to represent the complete and undirected graph of 5 objects, because you must ignore the fact that the symbol implies different magnitudes on the connections. And the complete and undirected graph has equivalent magnitudes of all its connections. In order to create a geometric representation of equal connection magnitude, you have to go to 4 dimensions, where the 4 simplex perfectly represents the complete and undirected graph of 5 objects. So 4D is kind of like the golden dimension, because the simplest n-dimensional building block of any A, D, or E lattice is the n simplex for that dimension, right? So it's not surprising that the 4 simplex dihedral angle is golden. Above, we discussed the deep golden relationship between D4 and E8. It also is not surprising that this golden dimension 4, when related to E8, group theoretically decomposes the Gossett polytope into the golden number 10. So next, so you know, I'm a fan of golden things.
What was that phi expression there?
Yeah.
There you go.
Okay, that's exactly 10.
Yep.
Surprising.
Because, yeah, that's 2, 5, minus 1.
All right. So you can kind of see that I have prejudices here, right? I have a prejudice towards E8. I have a prejudice toward octonions. I have a prejudice towards anything golden. But it's not romantic. You know, I have 11 years of rationale that I've built up on these things, and you guys do too.
Okay, if you can go to the slide before to add a remark for Richard. So it shows you that 5.
Extract the square root of
Oh,
5.
it's a 2 pi minus a 1.
Let me
No, that's
make
so
my remark. It shows you that 5 is a square in the ring of golden number.
Yeah.
Yeah, and that's what is very important.
Yeah.
5 is a square.
5.
5, yes.
Yeah.
And 10 is times
Yeah.
the square.
All right, so let's now discuss this idea, this phrase that I'm introducing here today for the first time, called cycle particle. And I'm going to cover 3 examples in 2D, 3D, and 8D. So we're going to take the root, we're going to start in 2D, right? So we're going to take the root polytope of the A2 lattice and cycle one of its subsymmetry groups, which is an equilateral triangle. Now we're going to cycle in the opposite sign value. All right, that's the 2D cycle particle. They're not complicated things. But you have to, but I believe you should think about them. You should decide on which cycle particle you want with a mind toward group theory. So now let's do a 3-dimensional cycle particle. I didn't have time to animate this one for you. So the essence of our 20 group is a tetrahedron 5 compound, first of all. And the reason for that is because orientation is more fundamental, at least in our context, than translation. And if we were to translate each of these 20 tetrahedra such that the centroid of each tetrahedron is coincident with the centroid of the 20 group, then sets of 4 tetrahedra converge into blue, green, yellow, red, and orange. And you get exactly the tetrahedron 5 compound, which corresponds to the dodecahedron. That is, its convex hull, defined by the outer vertices, is the dodecahedron. Each of the 5 4 groups, right, becomes a tetrahedron. So now A5 acts on the dodecahedron by permuting the 5 inscribed tetrahedra. I could call my particle a permutation, group theoretic permutation particle, but I like to call it a cycle particle. So even permutations of these tetrahedra are exactly the symmetric rotations of the dodecahedron and characterize the A5, which is less than the SO3 real correspondence. So we could call the cycle particle, as I mentioned, a permutation particle, or we could not use the word particle at all. I just like cycle particle. On an n-dimensional supergroup, we may cycle an n-dimensional subgroup. And that's what we did with the 3D case, right? We were in 3 dimensions as the supergroup, and we cycled its 5 3-dimensional permutation objects or subgroups. So we stayed in the same dimension. But we can also, and we did that in 2D as well. But we can also cycle an n-dimensional supergroup with its n minus m dimensional subgroups. So let's try that in 8 dimensions with a cycle particle and use n minus m equals 8 minus 4 to cycle a 24-cell subgroup on a Gaussian-Polytope supergroup. I don't have a good visualization for this either, so I just made 10 of them. So we can use various algebras to describe the cycling, such as Clifford algebras, where we can use Clifford rotors, we can use reflectors, we can use matrix algebras, and so on. However, I want to describe these cycle particles with an eye toward the idea, the notion of simple iterative programs, number 1, and group theory. And we're going to find out it's going to tie in almost an unexpected way to number theory, but not yet. So we have shown 3 examples of cycle particles at rest, right? Nothing was propagating. We can easily write a simple program or algorithm to describe the cycling at rest. So now I would like to talk about the program enhancement that would be necessary to helically propagate a group theoretic cycle particle. As we understand, propagating a cycle particle allows us to continue the cycling while changing the coordinate each cycle step, right? You all know what I mean by that, I guess, right? It doesn't matter whether you're translating, you can still count your cycles. I verbally and diagrammatically explained to Ray a helical propagation program that I needed him to help me program in a computer in 2 dimensions. So Ray programmed it for me, and I'm going to show you its output after a large number of iterations. But let me explain it to you first. Our initial condition is where I just take an arbitrary vertex of the A2 lattice, which is here, and I focus on the root vector polytope, which is my supergroup, okay? And I'm going to cycle its subgroups, which are the equilateral triangle. So I'm going to make a program now to cycle, to move, to have my cycle particle move in a zigzag pattern, which is why I put quotation marks on two-dimensional helix, because of course it's not a helix, it's a zigzag in 2D. I want to keep it rotating, so that each update step on its propagation path, on a zigzag propagation path, it has to keep rotating. And the simple program has to describe that. So let me explain the program. First, I tried to understand the multi-scale number system for my vertex-to-vertex moves for my cycle particle. So around a vertex, at our origin, we have 6 root vector directions upon which we can hop in a straight line in a scale of increments of 1. And then if I rotate plus or minus 30 degrees from one of the 6 unit scaling directions, it brings us to a scaling of the integers 1, 2, 3 times the scaling value for that direction, which in this red line case is half of the square root of 3. So I have 6 directions that we can move in this scaling value here. So notice that the blue and the red hopping would not zigzag propagate the particle. They would just go in a straight line. So I divide this 30-degree span from blue to red by 2, and I draw a division line here in gray at 15 degrees positive from the blue arrow. And then next, I place black lines perpendicular to that gray arrow on all vertices within the 30-degree span. So in other words, anytime I see a vertex, I'm going to place a black line perpendicular to the gray arrow. And now I can begin the program. We will draw a line from the origin to each sequential vertex on each successive perpendicular black line. Each of the lines makes contact with an infinity of points, but each one is at a different scale that is greater than that of the blue line and the red line.
What does that mean?
So the distance, the scale here is 1, so I can hop in increments of 1. The scale here is increments of the square root of 3. So I can hop 1, 2, 3. I can hop from here to here to here. I can hop in increments of 1. Here I can hop in increments of half the square root 3. All other hops in this infinite set of scalings is larger than the units of red and the units of blue. So there are cases where the length of the line from the origin to a point on a black line is shorter than the distance from the origin to a point on a black line that is closer to the origin. That should kind of be obvious to you why. And it's because the length depends on the angle of the propagation direction relative to the perpendicular black lines. In other words, it depends on where, right, on this black line, the point makes contact. Does everybody get that? In other words, if I'm going to make contact here where my arrow is, then it's possible that the previous point of contact, it's possible if I make my contact about here on this line, then my previous point of contact on this line here could have been like right here. And in that case, the distance from there to there would actually be longer than the distance from here to here, even though this point is happening later. Does that make sense?
Yeah.
Okay.
As long as you get 2 consecutive lines that are close enough together.
Mm-hmm. So my program spits out all this data, and then when you see it as, so my algorithm has order in it, okay? So I know that my data is gonna have order. But of course, looking at the raw data, of course, you can't really see the order unless you're a genius or something. The red points are integer distance from the origin, where the rays begin at a prime that is congruent to 1 modulo 6. For example, 7, 13, 9, 31. So if we like, we could restrict a two-dimensional zigzag helix here to just the red points that play on this prime number related values. And we would still have an oscillating zigzag path. So this graphic here obviously reveals more order from the algorithm than you would notice from that list of numerical values on the other slide, right? But there are other representations of this simple program that give even richer forms of order, such as interference type patterns. And this is the algorithm that I just described. This is one representation of a very large number of iterations of its behavior. And here's another representation of the same. It's the same exact type of representation. It's just with different colors and rotated 90 degrees. That allows your eye to kind of pick up on strange and interesting patterns that were kind of unexplainable or not predictable by just looking at how simple my program was. So this program generates a set of points that have an unexpected number theoretic quality. As I mentioned, specifically multiples of primes congruent to 1 modulo 6. They are a subset of the path and have the same property of oscillation as the total path, but a different point density. Now, each of these 30-degree sections is a mirror of the other 30-degree section within the same equilateral triangle. So that means we have 12 different mirrors, kind of like a kaleidoscope. So think of it like 2 mirrors for each of the 6 root vectors. And each mirror has an infinity of directions with different scales. So if we write the same type of program for the A3 lattice, then we would have n mirrors for each of the 12 root vectors in the A3 lattice. So I don't know if n is 2. It's 2 in 2 dimensions. I don't know what it is in 3 dimensions. And if we do the exact same thing in the E8 lattice, because remember, the E8 lattice is simply a network of triangular A2 lattices. So if we did the same thing with the E8 lattice, then we would have some number m mirrors for each of the 240 root vectors. So it has to be an integer multiple of the root quantity. So we can modify our cycle particle Walker program by using the full dihedral angle of the n simplex. So notice here I focused on the dihedral angle of the n simplex to identify, to decompose and think this through. And we can, but once we go into 3D, 4D, any of the higher dimensional root lattices that are composed ultimately of n simplexes, then we can do the same type of form that I did by focusing, starting with your span as a dihedral angle greater than arc cosine 1/2. So if we did this in D4 with the 4 simplex as its simplest building block, then in that case, we could use its golden dihedral angle to make a 4D helix. So it's a zigzag, but helical. It's a helical zigzag in 4 dimensions. So in dimensions higher than 2, we have more options on the dihedral angle that we can build our Walker helices from. So you could do this same form in E8, for example, by dealing with the dihedral angle of any of the sub-simplexes. So before discussing quasicrystals, let's discuss deterministic and non-deterministic algorithms. As I mentioned, any program or algorithm can be modified with the Hinge variable. When we run all the solutions for C using the Mandelbrot function, and we look at them as a list of complex numbers, then of course a normal human brain cannot discern any pattern by just looking at all of the solutions of C. But when we plot millions of points as the representations for the solutions of C, that some show up in the convergent set and some in the divergent set, well then, and kind of only then, do we see marvelous emergent pattern, and only with sufficiently large iterations. So you have to look at it the right way, and you have to do it a certain sufficiently large number of times. And this is because at the end of the day, the quadratic function, which is a simple program, has inherent order. It not only has order as a function, but it not only has order as a simple piece of written structure, but it also has different order under very large iterations. So insertion of a Hinge variable or syntax element into a program or algorithm renders it non-deterministic. A random number generator or intelligent chooser may exercise the syntax freedom. And neither one, the random number generator nor the intelligent chooser of the syntax, will completely destroy the emergent complexity. But a random number generator acting on the syntax adds noise to the emergent pattern. This is a plot that Ray made for me, which is the insertion of a Hinge variable operated by a random number generator into the Mandelbrot function. It's interesting that blurriness and noise are what the principle of efficient language would opt for, and what quantum mechanics is all about, in my opinion. The PEL, or principle of efficient language, is a core axiom of ours. It's well defined, and I think it's elegant. It says that the universe is of finite intelligence, and it self-actualizes itself as a simple program with a language. It says that it will choose the most economical expression of itself that it can think of, given its intelligence. Economical, of course, requires an objective, something you're trying to achieve, and then a quantity that's being used to achieve that objective. So here, the objective is reality, right? The simulation, physics. And part of that reality in the PEL paradigm is the emergent intelligence of the universe and all of the parts organized to actualize itself. And the economized for quantity is consciousness itself, the universe. So we have explained how consciousness is a network of choices of things to be aware of and things to relate to other things. When I say we have explained, that means in that series of those 4 papers that laid down a kind of QGR axiomatic ontology, it was discussed. But I'm going to review it very briefly here for you guys because you may have forgotten it or not really understood it or whatever. So accordingly, the elemental action of consciousness is choice. And choice can be quantized via the nasty word to some called reductionism. So I'm a reductionist and I'm a systems theorist. So I'm extreme on the systems theory, emergentism, and I'm extreme on the reductionism. I like to kind of oscillate and think about both extremes. This may not be convincing to you what I said about how consciousness is choice, but let me just philosophize with you here for one moment off of the slide. Look, it's philosophy. Consciousness and all this stuff, it's philosophy. So it's never going to be something that I can give you as a proof. But I submit to you that consciousness is not a stream of concatenated thoughts or ideas or objects. It's a network. And it's a kind of evolving network of ideas. In other words, it's not one-dimensional, like a string of zeros and ones. It's more like a network in your mind of all of the things that you're experiencing, feeling, subconsciously experiencing, and so on. But at a subconscious level, you may have a notion of choice. In other words, right now, I am freely choosing with my free will what to think about, what words and what images in my mind and concepts, and I'm trying to concatenate, right? I am doing it for you in one dimension, right? Because English is kind of one-dimensional, but English is also non-local. In other words, you're reading a novel and you're reading something, and then only later in chapter 4 do you realize a story arc that relates you backwards to something in chapter 1. And so it's this crisscrossing non-local network. It's like a non-local one-dimensional network generally. But perhaps in the real mind, it's not best represented one-dimensionally, right, in a real consciousness. But I propose to you that choice at a subconscious and conscious level is what you do as you concatenate networks, okay? You choose them, and that network of choices is a thought of love or this or that, because you can decompose love into other thoughts and experiences, and some of those you can reasonably say are simpler thoughts than others. So I'm going to go reductionist on you, right? I'm going to go medieval style reductionist, reduction hardcore, and I want to reduce choices. And you may have recalled me saying that, all right, so let's say that I place every choice of thought into David's mind that he could possibly have, every choice of feeling, experience, thought, I am putting it into him like a vessel. And I'm, by definition, blocking any of his choices of what to think or what to relate. Now, if I were to truly do that at a perfect level, then one could say that if they want, philosophically, that David is conscious, but he's kind of a mirror of my choices and the thoughts and relationships and feelings, experiences that I put in him. So it's kind of like I was the one making the choices. So he's like a mirror, a reflection of some set of choices that I did. And when I think about my dreams, I think, well, when I write a story or I choose a thing to think about or a way to relate things, I do believe I'm doing that by free will. So my conscious experience feels some of it, or I believe ultimately all of it, choices, but a lot of the choices may be subconscious choices, because we normally think about free will and choice with respect to the word conscious. But what about the vast, under the tip of the iceberg world of the subconscious? Would we default guess that that too is choices of what to subconsciously think? Like in a dream, when you dream, maybe you're making subconscious choices to create that network of relationships and symbols. So I like to imagine consciousness as related to the free will of what to think about, what to be conscious of, what to be aware of, what to believe, what to have as a mental experience that you define as consciousness. And I'm always somewhat humble about this, and almost every time I talk about consciousness, I find the need to remind the person I'm speaking with that, hey, I don't know for sure what consciousness is, but I also am not alone, because I don't think anybody has a solid enough definition of consciousness to get a strong consensus in their community of peers. There's a lot of argument and confusion. It's a very blurry thing. But whatever it is, I think it has something to do with choosing what to relate, what symbols to focus on, what things to be conscious of. Okay, so if that were the case, that it has something to do with choosing what to be aware of, then as a reductionist, I want to reduce to the simplest quantum of choice. In other words, I want to think about the choice that is the simplest possible choice that I can make. And of course, I'll tell you where we're going, to the binary choice, okay? But the binary choice between what and what, right? So let's do that for a second.
Click on the top one again.
All right.
You
All right.
skipped it.
Okay, so we're going to start by realizing that there are two things that we must choose, that we must reduce to: a quantity of things, and we must reduce to a type of thing, to be reductionist about the simplest quantum of choice, which is equivalent in this worldview to a quantum of consciousness. So what is the simplest okay, so what is the simplest quantity that one can choose from? It is 2, right? So we can choose on or off, A or B, or any number of choices of 2. So that's because even if you have a choice of 1, you can say, well, I ain't gonna choose. Well, that was a choice not to choose, right? So it still is binary at the end of the day. That's the end of the road in number reductionism. So what's the end of the road in object reductionism? Well, that's a coin toss, in my opinion, between the empty set or the dimensionless point. Perhaps at a deep level, they can be seen as the same thing. But regardless of the philosophy that people would argue about whether the empty set as an idea in the universe of all ideas is a simpler idea than the idea of the dimensionless point, that's just philosophy mumbo jumbo. I've listened to arguments. I can't really make a determination, but because it doesn't matter. So I'm just going to go with the point, because for me, I need to deal with connections. And I like connecting points more than I like connecting empty sets. But I have a feeling that some mathematician somewhere has probably written down some idea that a point is somehow isomorphic to an empty set. All right, so that was pretty primitive and almost naive sounding, but the simplest choice is either the choice of this empty set or this empty set, or it is the choice of this point, or it is the choice of this point to be on or this point to be off, right? You're down near the bottom of the barrel when you're dealing with dimensionless points, empty sets, and the number 2. And you're a big, fat, giant emergent consciousness, and yet making a binary choice of a point to be on or off is not beneath you, right? So us as these vast consciousnesses, we can choose to concatenate higher dimensional networks of symbolic relationships and cross relationships between hierarchies, and we can call that our emergent consciousness. Or we can get down to something ridiculously simple, like a point to be on or off. Quasicrystal simple programs can move a center emperor around in the hyperspace or the projection space analog. And you have to choose, you must choose to consider all the points you are dealing with in the higher dimensional lattice. For each, for the CE game, right, or program, you have to decide for all the points that you're dealing with, which ones are on as the CE and which ones are off as not the CE. Of course, executing a binary choice on one lucky vertex automatically defines all other points as automatically being not chosen. So you kind of don't have to do extra work to run around the E8 lattice and binary choice every single point. You just binary choice on one, and that equates to a binary choice that all others are not the one, the center emperor. I may have mixed some slides around here, because it feels like a train of thought is branched off because this was what we covered. But I'll still say this slide. So the amount of noise in a program like this, so the amount of noise in the ultimate pristine pattern from the algorithm not modified by a random hinge variable depends on how significant the contribution is from the randomly acted upon hinge variable free syntax step. In other words, you can imagine a very large algorithm with 30 characters, and you've just got a little hinge variable somewhere in it. Or the hinge variable can have different magnitudes of impact on the output, even if it just appears once. The PEL is interested in creating itself. Right? Or the universe is interested in creating itself economically, not in some wasteful attempt at ideal Planck scale resolution. In other words, itself is an emergent epiphenomenon, which includes the collective consciousness, your consciousness, planets, and particles. It is more economical when it comes to irreducible code actions for it to express the information. That is, the emergent information is what it's trying to get at. It almost doesn't care very much about the little mathematical pixels, right? So if it can express the power of the emergent information of you, your body, an electron, as an approximation, it uses less of itself. Right? It uses less of this commodity. Remember, we put out these two things to define economical: an objective, which is the universe or the physical reality, and the meaning of the physical reality, and then the irreducible actions that it takes to do that. So we've reduced our irreducible actions to binary choices on points. So the PEL philosophy says that in given these two choices, really, really fine-grained resolution that doesn't really change, like if you let it get blurry or random-ish down there, if it doesn't destroy the emergent information that is FOM, then the PEL is going to default to that. Be like, if I can get away with it, I'll take it, because I need to conserve more of myself. Why would it want to conserve more of itself? Because it wants to. In other words, why does it want to exist? Why does reality want to exist? Why does the universe want to be? Why do you want to do anything? When you're dealing with questions like that about a consciousness, it is because it is. You know, it exists because it is. So, and if it can do it economically, it can have more existence. In other words, it can evolve more for a given finite quantity of choices. That is why the PEL philosophy is grounded in a non-infinite universal consciousness. It may be possible for that universal consciousness to infinitely reach toward the infinite, but for the PEL to even make sense, the universe has to be a finite resource at any given stage of its evolution as a universal consciousness. Okay, lots of philosophy. So simple programs that lead to emergent complexity include the one I made, cellular automata of a huge family, abstract hypergraph programs like the space Wolfram is exploring, quadratic functions, and so on and so on. The universe of non-deterministic simple programs, though, is just as large as the deterministic set, since all deterministic programs can be modified with the Hinge variable, and also modified in more than one way. So it may be a larger infinity. There is also a universe of probabilistic simple programs, wherein a spread of weighted probabilities is generated as the output instead of some specific random or deterministic evolution update or output. Now, let us discuss using simple programs to translate and rotate our projection window around in E8 to pick which vertex with its empire gets to be the lucky center emperor for that update set to the inflation possibilities space in lower dimension. Now remember, I just said that any of these programs include another infinite set which can be modified to be probabilistic spreads. So when we say lucky here, what I have in mind is not that any one CE is definitely picked, but I want in the evolution of the simple program in E8 to have a weighted probability spread. So I want to think about practicing and getting our hands dirty with three classes of simple programs to operate on moving things around in a lattice. The deterministic class, the class modified by a Hinge variable, and then the class that gives probabilistic spreads. We're going to project a single 24 cell from a gossip polytope to R3 along an angle that transforms it into a 4 group of tetrahedra with the 13th point at the center. Let us focus on 10 orientations of 24 cells in the E8 lattice. We will use a 4D projector to send a slice of the E8 lattice with only one orientation of 24 cell to 4 dimensions, where all these 24 cells will still be 24 cells, but they'll be scaled down 24 cells. They will be Fibonacci grid spaced in 4D. And that will be 1/5 of the Elser and Sloan quasicrystal. So we can skip 4 dimensions and project these 24 cells of a single orientation directly from E8 to 3D, where they will be fifths of 20 groups that are all Fibonacci chains spaced from one another. So we want to use our window translation program or algorithm in E8 to select the center emperor, which is the point at the center of a 24 cell, right? That's the 8-dimensional aperiodic zigzag thing. And then our window can be the thickness of the gossip polytope if we want 2 sizes of 24 cell in 4D, or one size. So we can have any number of sizes of 24 cells, but if we're just talking about one unit Gaussian polytope, then half of it as the thickness of our window gives us an Elser-Sloan with just one size of 600 cells and one size of 24 cells. And if we use the full width of the Gaussian polytope, then we get two sizes. And we can do the same thing in 3D, where if we skip 4D and shoot straight from our 24 cells to our 4 groups, then depending on the thickness of our window, we can recognize 1 or 2 sizes of the 4 groups. So when we want to cycle to a different orientation of 4 group or 24 cell in our inflation possibility spaces in 3D and in 4D, then we will rotate using a Clifford rotor, probably, our projection operator. So we're rotating it and we're translating it according to a simple program. So for me personally, nowadays, I need to understand how we can see an assembly space where we project one 24 cell from E8 to a 4 group, and then rotate our projector to project another one with the centroid at the same location as the first one, but its other 24 points converging into 12 points in 3D, such that the second projection of 12 points lands its 4 group rotated by 15.5 degrees from the first one. So we've done a lot of work on that, and I've forgotten the explanations, and we don't need to stop now to talk about it, but for me, all I'm saying is, I'm still blurry on it, and I need to review what we've done and talk. Maybe there's more work that we need to do on it, maybe not. So 120 of the 240 points correspond to a 24-cell 5 compound in 4D and a 4-group 5 compound in 3D. So I would like also to understand how one set of 5 Clifford rotor actions map to the right chirality group and another set of 5 map to the left chirality group. If we could figure out how to make this work, we would have various aperiodic helical type paths in E8 that become richly complicated helical paths in 3D. So as the simple program translates along a hyperhelical path in 8D, it is choosing a new CE in 8D for each iteration. At each iteration, it also rotates its 4-dimensional window to pick up a different set of 24 points on the surface of each new Gaussian polytope that it hops to, right? Which maps to a cycle particle in 3+1D, moving on some type of strange helical path. This is just a screenshot of the homepage for the Wolfram physics project. This probably existed back in April when we were on that Zoom call with them, but there's a growing library and archive and gallery. This community is in the thousands at this point, and I think it's a resource. I think it's a community we should at least temporarily participate in, along the lines of this summer school kind of thing that I said, which is, if this is the space that we're in, simple programs, maybe we should take the biggest group in the world of people, the biggest community that's thinking along the same lines as us, and their group and our group are very much alone in the world. There are not many others that are thinking so crazy that you can get fundamental things as emergent epiphenomena. So any complicated, so here's the book. So I bought a copy for all of you guys, and it's a big book, but I was gonna give all of you guys a copy of the book, including Dugan, and talk to Fong about whether or not we want to take a couple weeks of a sprint to just put everything on hold and just saturate ourselves in what the hell this community is doing and why Stephen Wolfram and these mathematical physicists, those two guys in particular, why they're so excited about something that relates to general relativity and quantum mechanics. What did they do? What's going on? So we'll talk about that. I don't want to give it as a directive, but I did order the books. So in some sense, Wolfram is trying to, encourage us to join the community. So it could be interesting, because who knows, if with his endorsement of what he said about us being the front horse on gauge symmetry, on really cracking the code and getting a really good program, maybe we could leverage and get lots of other people kind of jumping in and using our math, taking the baton and running with it. And that would still put us in an important place, because even if somebody else makes a breakthrough, we're still going to be the most deeply, saturated people in it. So anyway, any complicated graph can be reduced to its minimal representation as a trivalent graph, like I said. The QSN itself, without any transformation, is already a trivalent graph, while the E8 root lattice is a 240-valent graph, which can be reduced to a trivalent graph. So there are various tools and documents and posts of programs that people have started doing in this new Wolfram physics project that's online. So we should join this community, I think, and see what we can learn from them. And we should take a couple weeks of the next sprint or some near sprint and just go hardcore into this and try to learn it like it's a class where we've got to get a good grade and just take it serious. All right. So to review, we have talked about simple programs wherein emergent physics results from large numbers of iterations, a very radical philosophy, easy to reject because how are you going to find it, Or how do you even know that the universe is a simple program in the first place? What if you're looking for something that doesn't exist? But we're going to restrict ourselves to simple programs operating on the E8 root lattice, and we'll explore cycle particles that propagate on hyperhelices. And all such higher dimensional quasi-particles will be in some sense local in their native dimension, but their representations in quasicrystal spaces will be in some sense non-local, and really be topological representations of the local patterns in the higher dimension. And my meaning here of local, non-local, and topological is that points of the quasi-particles in the higher dimensional periodic spaces are not rearranged. They just are where they are in the root lattice. But in the lower dimensional quasicrystal representations, things are significantly rearranged while still preserving information about their arrangement in higher dimension. As we create a pattern over many steps of moving a center emperor in either the higher dimensional or lower dimensional representation, we might be able to consider the paths that are traced out over time as forming a growing graph network that takes on increasing complexity over many steps. That's a little different than the quasi-particle picture. In that picture, you're evolving a graph, and then you can represent it in an abstract graph space like Wolfram does as an abstract trivalent graph, and just watch and see if you get surprised over many iterations on the pattern that it creates, and you just let it keep growing. And in that sense, it's a very different way of thinking about it than a quasi-particle, where with quasi-particles, you're kind of thinking about one thing at a time. The last thing I want to say is the shell model idea. It's not talked about by me in detail very often. I don't critically discuss it with anybody. I've had very, very, very few discussions. A couple of years ago, I had a brief set of discussions with Fong and Cynthiana, and I mention it though, I say it a lot, but we don't talk about it. We don't critically vet the idea very often because I don't push it. But everything that we have talked about so far pictures the familiar notion of rectilinear projector boundaries and infinite quasicrystals, flat, infinite, or finite quasicrystals that are kind of rectilinear if they're finite, and if they're infinite, they're just infinite. But that's actually unnecessary, the rectilinear way of looking at it, or the infinite way of looking at it, because a quasicrystal can be grown with shell projectors, and information can be encoded by selecting which shells to project and which ones not. So I sent an email to you all about a week ago on this. Ray has done work on this that's related to this, and then Ray's done some subsequent work with me in the last week and a half on it. There's a lot of interesting critical thinking to be done about this shell model idea that I have. So I'm giving it an advertisement here. So the number of points on each shell will be approximately invariant at large radius. So as you're starting with the small growth, your number of points coincident with a growing two-sphere is changing radically from the origin to the next to the next. The numbers are changing significantly. But as you go out to very large radius, you can see the asymptotic pattern in that at a universal scale radius, and actually even radii way smaller than that, you'll notice that the quantity of shell of points coincident with the shell is now very, very, very large. But from shell to shell to shell to shell, at that level in the asymptote, it doesn't really change very much, the quantity. And this what I'm saying, it will become important later in the deeper discussions of the shell model. So any possible pattern of quasi-particle that anybody can imagine in the rectilinear approach, as we typically think about it, can also be produced using the shell model. In fact, at the end of the day, so I don't want to jump ahead here. So quasi-particles, so one of the important things about the shell model is that your center emperors are very, very large in number. So you have, the shell model is this. I'm in the E8, right? I'm at the Gaussian polytope, and I place a 7th sphere circumscribed around the Gaussian polytope at radius 1. And then I place a second 7th sphere with the same centroid as the first, but with a radius 10 times larger than the first. So now I have an 8-dimensional ring. That is the 8-dimensional boundary between, or the 8-dimensional space or set of points between boundary 1, which is 7th sphere at R1, and then I have this other 7th sphere at R10, and all of the points within that 8-dimensional bulk of those two 7th sphere boundaries can be projected down to a projection space. So then I can, if I want, I can say the next set of points that I want to lay down will be, I'm going to skip integer values. So I say, well, now I'm going to go to an 8-dimensional ring that is defined by the boundary of 7th sphere at radius 13 and 7th sphere at radius 14. And I'm going to send those points down. Now then those points will populate some internal to the first set of projected points. They'll densify in there. But they will also lay down some new points that grow the radius of my growing quasicrystal in the lower dimension, right? So I call that growing surface the action horizon. Now at a radius of the universe this large, you might as well think about the action horizon, from your perspective as being flat. It's pretty much virtually flat, right? Because at our scale relative to the shell scale where we're at now, it pretty much looks flat, even though there is technically a curvature. And the way that I encode programs on the action horizon, where everything, all the physical things have to happen on the action horizon, is I encode them by how I concatenate the selections that are free to me on the 7-sphere boundaries that define my 8-dimensional rings, that define what gets projected. So at the center of each set of 8-dimensional rings, there's a set of points which are at the center. So those are the center emperor points. So one of the powerful things about going to the shell model or spherical projectors, rings like this, is that now you're not dealing with just one center emperor, you're dealing with a large family.
Wait, can you say that again? At the center of the 8-dimensional range, that is successive sequence 8-dimensional
The
range.
center of the thickness of the rings, not the center of the rings,
okay.
right?
Yeah.
Yeah, so with a rectilinear, finite rectilinear thing at an irrational slope, there can be one and only one point at the center of height. But once you go, for example, to the Gossip polytope, defined by some shell that's just shy of the unit length by 1/2, and then a shell, let's say, that's another second 7th sphere that's at 1/2 from the points, the unit lengths. So at 1/2 and 1.1 of the unit length, now you've got an 8-dimensional shell of thickness, or an 8-dimensional ring. And then these 240 points would live at the center of distance between R1 and R2, the hyper thickness of the 8-dimensional ring. But we can make the rings thicker such that we have more points than just those 240. And those points would not be the center emperor, but they would get sent down to the projective space. Some of those points would be the empire of the center emperor set. So now the center emperor set is very, very large at large universal radii. Okay, so quasiparticles can propagate along a virtual infinity of directions in 3 space on the surface of the action horizon. A virtual infinity. In other words, as you all know, you can take the Penrose tiling and you can draw an infinity of directions that make contact with an infinite set of points at a certain power of the golden ratio. An infinity upon the infinite Penrose tiling. Now, in a universe of Planck scale shells that's this large, you would have a virtual infinity of directions that a quasi-particle propagation path can take. Okay, so, but if you were to say, I'm going to take a small duration of action in the universe, very, very small, right? Then all of the possible quantum states for your particles, like your game spin, your game charge, all your game fundamental particles and their quantum values over this very, very small sequence of shells is defined by not the bulk, it's defined by the surface area divided by some denominator that has part of its value defined by something like the unit or the Planck, the unit length of the lattice or the Planck distance, the unit length of your Dirichlet space and the possibility space. So it's going to be some equation that relates to, you know, pi and 4 and divided by some value that relates to the square of the Planck area, right? Roughly speaking. I'm deliberately trying to draw a correlation to the Maldacena conjecture, but I'm also, even if I didn't know about the Maldacena conjecture, just pointing out something that would be a fact about this picture that I'm painting of the action horizon being where the action is happening, because we have a universal scale clock, which is the growing radius of the universe. It's absolute and it's real, meaning at one Planck moment after the Big Bang, the universe was smaller than it is today. So this interesting directionality of time as radius or size of the universe is in this story the radius of a shell, the growth of how much the quasicrystal pattern has grown. And if you were to project it all at the same time, you get a deterministic giant thing like this. And that's not good. We want to encode, and we want a simple program. And therefore, with the shell projector model, the code ultimately has to tell you what the numerical digits are in these one-dimensional values, which is radius, right? So it's just a simple number that says, oh, I'm going to pick a shell, a 7-sphere A and B, or 7-sphere radius X and P. And then I'm going to skip some others, and so I'm going to encode. So the program is supposed to create emergent epiphenomena pattern, right, by some simple program that is defining the sequence of shells that you skip, right, the radii that you skip. That's a good way to encode. It may not make anything physically realistic, but it is a way, definitely a way to encode information. So the shell model provides the opportunity to move from the single center emperor picture to the n center emperor picture, where n is very large, at large radius. That's it. Okay. Perfect timing.